work as a scientist in the National Brain Research Center in Gurgaon, and now he has joined the Mathworks in the education team. So he's one of my colleagues. Am I audible?
1 minute, I have to
So
make his presenting.
Yes, sir, you're audible, sir.
Okay. Yeah, so if you could please make Truffle the presenter.
Yeah, 1 minute.
That would.
Yes, and now the professor is the presenter now.
Sure. Yes. Thank you. Thank you, everyone.
Welcome, professor, and you may start your session. The stage is yours.
Sure. Thank you.
Thank you.
Thanks for the introduction as well. I'll just maybe begin by sharing my screen and hopefully start right away. Yeah. So is the screen visible, Dhruv?
Yes, sir, it's visible, sir.
Sure. Great. Let me just move this to the other screen and yeah. So just some things like, I'll just get the chat window and everything populated on the other side so that, in case any questions pop up, we can pause, and if it's too long an answer, we'll try to kind of answer those at the end. But otherwise, if it's something short and it's relevant to that example, we can take it up. Sure. So, okay. All right. Okay. Dhruv has been muted again. All right. Sorry. So again, so Dhruv said most of you were from a background in electrical engineering or anything. Or on a similar background. So we'll take a couple of examples related to biosignals today, and we'll see how that goes. Okay. But feel free to kind of keep the interaction going from the past sessions, and ask a question whenever you feel like it. If I'm not able to answer it, I will see if we can answer that in tomorrow session or so on. All right. So the agenda for today is, I think I'll briefly go over some terminology again, and I think you've already covered deep learning for images, so we'll skip this part completely, and we'll jump right into deep learning for signals. All right. And at the end, we'll talk briefly about deep learning deployment, but not really in much detail. So I think you might have seen something similar earlier, wherein so we talk about machine learning as a general technique, which came up in the 1950s with the advent of computers themselves. In the 1980s, the statistical techniques working with data for deriving meaningful insights from this data came about. So this was where machine learning came to the fore. While deep learning itself has only been there in the past decade or so. It started, deep neural networks started becoming really popular only around the 2010 onwards. So it's been just over 10 years since they became really popular. Yep. So as you may know, deep learning is a subset of machine learning with automatic feature extraction. That is, it learns features and tasks directly from the data. So you have to enter that data directly to the deep neural network, and it does the task for you. If, for example, in this case of, say, a CNN, identifying what vehicle is there in image, so right from the image itself. So unlike machine learning techniques, you need not do any sort of feature extraction in these in deep learning. However, there is a caveat here. So feature learning or feature extraction might still be useful. We'll see that in the example. All right. So yeah. So deep learning performs end-to-end learning by learning features, representation, or tasks directly from images, time series, or text data. And instead of deciding what sort of features to extract and what sort of classification model to employ, what you're trying to use is a certain topology or certain network topologies, or certain neural network topology, wherein we specify the architecture of this neural network model, right? So these can be convolutional neural network or networks, or it can be another type of neural network called long short-term memory, and so on and so forth. All right. But does this mean that machine learning is no use at all? No, of course not. So deep learning is useful only if you have lots of data as well as good hardware to kind of work with. So deep learning is a very data hungry technique, and obviously it's also very computationally intensive. So only if both of these are satisfied, both of these conditions are satisfied, would I recommend that you go for deep learning. Otherwise, machine learning techniques might really be better for you, right? Again, there are ways to kind of increase the data, the size of the data you have. So you can do simulations and generate data. And I think hardware is less of a constraint these days, but again, that still is one of the factors you should consider when deciding between machine learning or deep learning techniques, right? So, okay, there is someone who says, I'll try and stop my camera. So, all right. Hopefully, anyone who is having bandwidth issues, I think hopefully this improves that for them. All right. So, and deep neural networks basically work like the human brain does, and you can most commonly you use it for classification or regression. So you have your networks arranged in layers, such as the input, hidden, or output layers. You pass your information in the forward pass while you adjust your weights and biases in a backward pass, right? So at each node, you are basically doing a very basic linear algebra operation. You are just multiplying it with a weight and adding a bias to it. All right. So this weight addition, this weight multiplication with a weight and adding a bias at the very least. So this is the most basic sort of neural network, uh, basic sort of operation which can happen at a node in the neural network. All right. So you might have also learned about deep learning enablers, such as the availability of public data sets, increased acceleration from GPUs, and the availability of world-class models, right? Yeah. So let's look at some deep learning applications. So you may have already looked at uh, a bunch of image processing applications, such as those from, like I'm sure you looked at image classification in the morning, and you also looked at finding, say, some transfer learning problems, right? So I'll focus on this last application here on the bottom right, from where the researchers at the University of Texas at Austin, they acquired magnetoencephalographic data, so MEG data. And this MEG data is essentially a representation of the magnet or the electrical activity in the brain. It has higher and it has better resolution than EEG, though, which you might have heard of, right? So this signal data is taken and we create a scaleogram out of it, which which is basically you're taking the signal data and converting it into a different representation. So in this case, you're going from 1D signals to a two-dimensional representation in form of a scaleogram. And this two-dimensional representation is given to your deep neural network. And what the application that the researchers were working towards is enabling ALS patients to speak, or decoding what they were trying to speak, rather. All right. So so this is so essentially the MEG data was acquired, processed, and given to the neural network, and the phrase that the particular subject was trying to say was decoded. All right. So it seems like almost mind reading in some form or the other, right? So this is just to highlight what is the sort of uh, extent to which deep neural networks can be applied, right? And and this was completely done using MATLAB and Simulink itself. All right. So to give you a flavor of, again, how deep learning might be useful across different domains, you use it for computer vision or image processing applications, but for applications like detecting parts of or objects in an image or denoising an image. But the same can be applicable to signals as well, wherein, say, there is a signal such as, say, an ECG, where there are very definite parts of an ECG. So so each ECGs or normal ECGs have very definite shapes. So you can use deep learning algorithms to isolate those shapes. You can use deep learning for denoising signals. You can use it for generating control data or control signals for your applications, as well as for text analytics, sensor data analytics, audio processing. So this might be something that you already use nowadays. So we all of us, we might have interacted with on these voice typing or these smart assistants in the form of, say, a Google Home or your Amazon Alexa and so on, right? So all of these use deep learning on signals in some fashion or the other, right? So that brings us to a brief overview, right? And we'll jump into the signals bit here. So any questions till now? So I'll just wait maybe 10 seconds for any questions, and then jump into more deep learning for signals. Sure. Sure. So let's go ahead. So this is a typical deep learning workflow, right? Which you might have seen earlier again in the morning. So we'll look at these 4 steps, right? So there is the access and exploration step, wherein you read data. The labeling and pre-processing step, where you work with these labeled data, which is or you label data yourself, or uh, you for your application. Then the third step is for the development of your predictive model itself, where you look at developing your models, doing some hyperparameter tuning and so on, and finally deployment to systems, right? So deep neural networks take in numeric data. So if you're working with images, those are a numeric matrix. But if you're working with signals, they are basically numeric vectors, right? So each number in this vector represents a signal sample, and the deep neural network takes in that. All right. So when accessing this data, so these are common challenges that you may face. All right. So you may face issues with accessing large amounts of data, so which might not fit in memory. Say you have data which is coming in from a sensor node, which is placed somewhere, like, say, maybe an air pollution sensor, which is placed at some remote location, right? So there might be tons of like a number of such sensors. So if the sensor node is relaying this data continuously, then very soon you'll run out of memory to kind of store all of it, right? Or to process all of it, rather. So So in that case, you'll have to come up with algorithms wherein you load your data only at runtime and then work with that, right? In other cases, you might not have enough data. So from data excess, you go to data scarcity, right? So what if you have an imbalanced data set and you do not have enough data, right? So in that case, you may need to look at techniques for augmenting your data or generating synthetic data, so to speak, right? And finally, this step would, how do you go ahead and label your data set, okay? And how do you do that faster? So in academics, in typical research or educational setting, we may focus on using readily available data sets, but creating data sets itself is a really good research problem to work on. And I definitely recommend, if you are thinking of, say, working on creating a data set of your own, if there is no data set available outside, definitely go ahead and, I'm sure like MATLAB and Simulink will go a long way in helping you do that as well. So as I said, in research, you spend typically a very little time working on your data set and most of your time on modeling and algorithm building. While in industry, it's completely the opposite. So industry spends a lot of time developing their data set itself and a smaller chunk on developing their model. Yeah. So you may have already come across image data stores when trying to read images. So in this case, when working with signals now, you can look at using file data stores or audio data stores. All right. Unlike images, so you'll be reading this data and then processing it after you get this into MATLAB. Right. However, these work very similar to your image data stores itself. So they basically act as a pointer to a particular file in a bunch of folders that you have. All right. The next thing, and this might be useful when working with signals, is looking at tall arrays, right? So tall arrays are essentially huge, as the name says. These are huge arrays which you can use for working with out-of-memory data, and essentially these arrays, or part of an array, a part of this tall array is loaded at runtime, and you work with that. All right. So in case you have, say, in case you have multiple CPUs or GPUs at your disposal, what can also happen is you can use these, like say so the algorithm can work on different parts of these tall arrays as well. Like say the first 100 samples are worked upon by the first CPU, while the next 100 or by the second, and the next 100 by the third, and next 100 by the fourth, and this way you can accelerate your entire processing. All right. So you may have come across image labeler or ground truth labeler or video labeler when working with images. So when working with signals, you have your signal labeler. And if you work with audio data specifically, or if you're looking to work with audio data, then you have your audio labeler as well. All right. So these appear again in the apps tab, which we'll look at shortly once we open up MATLAB. All right. So there's again a big image labeler which is there. So this is a highlight of audio labeler, labeling a particular signal, audio signal. So you can see it loads up the signal like how it would say it's just showing these samples. You can play them, pause them whenever you want. You can choose to apply a bunch of algorithms on them for detecting where are the speech segments and where are the non-speech segments. And then the speech segments you can go ahead and say so this is just a binary sort of classification here. So there is speech here, and there is these segments do not have any speech. And you can see there is one small chunk where there is some audio which is detected, right? So you can simply go ahead and extend this, and you can use this to label your signals. All right.
Praful, sorry.
Sure.
Just a
Yeah.
clarifying question about the previous one, if you could go back one.
Yeah.
So in the morning we mentioned what classification means,
Okay.
but we didn't mention anything about labeling. So if you could please elaborate on why this is important, that would really help.
Okay. Okay. Sure. Sure. So as I said, uh, so you make there are a range of applications which are possible with machine learning or deep learning, right? However, like if say you were going about creating your own application, or if say you were thinking of uh, uh, of working on your own research project, say that research project is something like monitoring the condition of industrial motor, all right, and based on some vibration data which is coming off of that motor. So you might not really come across a data set which describes exactly which gives you that data, which gives you this this entire sort of you know uh, uh, you might not come across a data set which is useful in this case, right? So you may need to collect data by yourself and then go ahead with your machine learning or deep learning application. So this is where these labelers come in handy. So if you were going to label, say, what part, say, so some say you were collecting your vibration signals. So maybe you collected these signals during the normal operation of the machine, and when the machine was overloaded, say the motor is overloaded and it is straining to kind of turn, then the vibration signals change. So if you could uh, use these um, sort of differences to label this data set, so then labelers become really important. So in you also have, like, say, image or video labelers. So say if you were working on something like automated driving or something of that sort, so wherein you may need to detect vehicles in an image. So you can go ahead and see how you can choose to identify objects which appear, and you may want to kind of add to these by creating a data set which is relevant for your setting. So maybe data sets which were created on roads which are typically in the US or UK or wherever might not really work on Indian roads, right? In that case, labeling and creating these label data sets become really important, right? So please go ahead and ask any questions regarding labeling. So as I said, it is again an area of huge interest. So in case someone's interested, then I can definitely speak more on this. Yeah. And what if you do not have enough data, right? Or what if there is data imbalance? Okay, can deep learning label things by itself for future reference? Yes, it can. So if let me just go back to that image labeling slide, and yeah. So yeah. So if you see here, there are some, this is a image labeling example. So you can say, go ahead and create your own labels first. So say you label this, and then you see here, automate labeling option. So this automate labeling option is basically you applying some automated algorithm which can detect objects by itself. And very often these are deep learning algorithms itself, or they might be simple computer vision algorithms as well. So it's like once you train a good enough sort of a small model, you can use that to kind of build more complex models, right? Or train data for, or create this label data set for more complex models. I hope that answers your question, Ashish. All right, great. Yeah. So let's see. Yeah, so this is like a automated vehicle detection algorithm. So these are, I think, some of these algorithms are already available in these labelers, but yeah. So as you can see, you can add your own algorithms here. So you can create. So basically, it's like adding a function. It's nothing more than that. You're simply writing a new function and adding it to this list. All right. So let's go ahead and yeah. So what if you do not have enough data, or if there is data imbalance instead? So in that case, you can use augmentation techniques. So you can say do data transformations. The most simple sort of transformation in case of signals is like creating copies of the signal. So say you have say you have an imbalanced data set between say normal and abnormal data. So like if we take the same example of condition monitoring. So say you have the signals from the machine operating normally for 100 hours, while abnormal operation, so you only have 10 hours worth of signal for the abnormal operation. All right. So the most easiest of a data augmentation technique can be you take that 10-hour segment for for the abnormal operation, and you kind of just create copies of it and concatenate it to get like 100 hours, right? Whether it is useful or whether it does help you detect these abnormalities better, so that might be suspect, but you can definitely go ahead and do this, right? Another way is to kind of create transformations, such as say add some noise to this 10-hour abnormal data, and because abnormal data in other cases might be similar in nature, so you're just varying, you're getting this abnormal, like additional abnormal data by just adding some sort of noise to it. All right. You can also go ahead and you may have come across GANs or adversarial networks, which kind of create data from noise itself. So in this case, so these GANs started from noisy pixel samples and went ahead and created these images of faces from a combination of images which were given to them earlier, right? So the next option, when you have when you do not have enough data, or it's just maybe complex to kind of collect this sort of data, is creating models or creating simulation models to create to generate data, right? So so you can synthesize data by creating models of in Simulink. So this is very useful, as well as this is used widely. Specifically in I've seen it being used widely in phased array or communications applications. So say you were trying to detect objects on say you were trying to detect flying objects from your radar signals. Okay, so in that case, you know, that object, a flying object, can be, say, a commercial aircraft, but it can also be a military aircraft, or it can be a drone, which is maybe big enough to kind of appear there, or there are a variety of such aircraft, right? So you can't always fly an aircraft and try to kind of capture the radar signals off of that to identify it, right? So in that case, you may come up with like models which simulate what sort of data can be generated due to a particular target appearing on the radar, right? Or in case of communications, so instead of going ahead and if you're looking at something like identifying modulation schemes in different communication networks, like say for a 5G network, if you're trying to detect like say if you're trying to detect if you're trying to collect 5G data itself. So in that case, you can go ahead and simulate this, and and go and use that for your data collection rather than for rely on actual on the field data collection, right? And in that case, you can kind of also vary a lot of these parameters, like say you can vary things like fading, or vary imperfections which are introduced in this signal due to the channel, due to the communication channel, or due to weather, and so on and so forth. All right. So any questions here on data generation for training?
I think they're okay. I think we're mostly dealing with beginners, so maybe if we show a few examples, it'll be easier to understand.
Sure.
Maybe we can skip ahead a bit to the hands-on.
Yep. Sure. Sure. So let's maybe open up MATLAB itself, and then go ahead and let's start right away with the examples of it. Yeah, I think. So I think then we can maybe return back to the slides and go ahead with what was there. So let me show you a bunch of things which appear here. So in the apps tab, you may have already looked at Deep Network Designer in the morning. So if you just go ahead and type in label, you'll get all of these options for your audio, signal, and image labeling. There's also video labeling and ground truth labeling for your applications. And if you're working on automated driving using LiDAR, then you also have a LiDAR labeler. Okay. So you can go ahead and explore these, or documentation on these is if it's useful. All right. So we already saw Deep Network Designer. You might have already seen Deep Network Designer. Let me open that up, and then let's look at how we can start by designing a neural network for processing signals. All right. Yeah. So while Deep Network Designer opens up, let's look at how we can go about selecting a particular network architecture. So you already have seen how you could use CNNs, convolutional neural networks, when working with image data, right? So when working with signal or text data, you can use CNNs, or you can use another type of neural network called LSTM, or a long short-term memory network. All right, we'll have a brief idea about what LSTMs are, and we'll talk about that. But you can also use the CNNs like what you had seen earlier for working with this. All right. So you again might have the question like what might be a good layer to use So if you're, as I said, if you're working with sequence data, you might use LSTM layers or bi-LSTM layers, and the research papers as well as documentation examples in MATLAB itself can be good guidelines to begin with, and then building upon them, right? So yeah, why are these appearing here? Just a second.
Yeah, so we looked at the convolution layers in the morning, the 2D convolution, max pooling, ReLU, softmax, and fully connected layers. So
Yeah.
LSTMs will be new for them.
Sure. Sure, Dhruv. I think so. Let's jump right into it then. Yep. So if you're looking at signals, then your signals, either you can look at, say, something like using deep learning for event detection, say something like detecting Hey Google or Hey Alexa. So detecting keywords like that which trigger an action. So you can use something like that. So you can also use it for signal segmentation. So I already mentioned, like, how ECGs have a very typical shape, and you can use deep learning to segment different shapes. That is, say, there is a small bump in the beginning known as a P wave. There is a spike known as the QRS complex, and then there is another bump called the T wave. Okay, so you can. It is very useful for physicians to detect how long each of these wave segments are, and it is difficult to do this manually. There are signal processing methods to do this, but machine learning or deep learning can take this to an entire new level, right? You can also classify signals, say detect whether this signal data belongs to a normal mode of operation for a machine or an abnormal mode of operation, or detect whether there is a pathology present in case of, say, maybe using ECGs for humans or so on, right? And as I said, you can use it for denoising applications. So you can see, so if you can denoise signals, remove the noise component of it. And if any of you are familiar with the cocktail party problem, as in where there are a bunch of noises which are overlapping with each other, and you have to, say, isolate these noise segments from each other, then so this sort of a source separation problem. So you can definitely isolate all of these overlapping signal samples from each other. All right. So as I said, you could use LSTMs or CNNs. Let me just highlight LSTMs here before jumping into MATLAB and doing this. So doing this is like really useful, because signals are very different from images, and it would be useful to go over this in slides instead of inside MATLAB. All right. Yeah. So as I said, so LSTMs, there are typical signal processing architectures. So you can use LSTMs. Basically, you have, say, sample data which is incoming, and you're giving this into a signal. All right, giving this into a network, and basically you're giving these samples one by one. All right. Or you could also see if you want to give these samples along with features, right? Even though I said earlier that you can deep learning is typically end-to-end learning, but if you extract features and provide that to the network, you can see that that also makes a really good difference to to your signal processing architecture. All right. And the other option is to use CNNs. So you already saw CNNs in the morning, right? So typically you have your convolutional layers, your ReLU layers, and a pooling layer, and a bunch of these layers are repeated until you have a fully connected softmax and a classification or regression layer, right? So these took in images, right? So you may have you looked at transfer learning problems earlier. So what you are doing is you are taking a one-dimensional signal and representing it in 2D. So you are creating, say, a time frequency representation out of it. All right. And so this time frequency representation or this two-dimensional representation, you can simply give as an image to your deep neural network. All right. So any questions here on these two? Like, how do you generate the? Is it clear how we generated this time frequency representation? Sure. So yeah. So if why are there repetitive units in CNNs? Okay. All right. So yeah. So repetitive units are there. So it goes back to sort of like, you know, it goes back to so think of if you think of if you try to think of CNNs and try to get an intuitive understanding of them. So you can think of these three layers as detecting some sort of higher level features, some lower, like whether, so you have convolutional filters which detect whether, say, a particular variation is present or not. You have ReLU layers which identify whether that filter output was high or low or absent. And then you have pooling layers, which are basically like, you know, downsizing or downsampling your data, right? Or say maybe say reducing the size of that data, right? So basically, so you can think of it as the first layer doing one sort of detection of these events, and the next layer is just doing that on these outputs. So your classification problem might very well work with just one layer, one such layer, like one convolutional ReLU and pooling layers. You don't really need 4 or 5 such repetitive units, but adding such units adds to your entire sort of your classification accuracy, right? So before deep neural networks came about, this was a fundamental problem in neural networks themselves. So people were, so in that case there weren't these specialized layers, but you know, people asked whether you know, having too many hidden layers, too many intermediate layers, did it help at all? So another way of looking at it is another way of looking at it is like, you know, as Dhruv said, the more layers you have, the more information a network can store, and the deeper features you can extract. So essentially, if you were thinking of, say, like you know, if you're thinking of, say, just 2 features, and you were trying to classify between different classes. So what neural networks do essentially is to map your initial data to an n-dimensional space, and this n-dimensional space is sort of represented by this intermediate layer. And so whatever is not separable in this, say, in the 2 feature space, which can be like, say, 2 inputs coming into the neural network, it becomes separable because we have created these layers, in intermediate layers here, right? All right. Yeah. So yeah, let's jump into maybe the classification problem now, right? And we'll go back to that if we want. Yeah. So we'll look at ECG classification, and we'll look at using LSTMs for classification. And as I said, we'll also perform some sort of preliminary engineering, feature engineering, and see if there is any difference in result. All right. Let's jump right into MATLAB. And many of these are like shipping examples itself. So you know, we can jump right ahead and do this. So if you look at the MATLAB drive link that we had shared earlier, so you may have gotten example such. You may have gotten a sort of folder there called classify ECG signals. So if you want to follow along, you can simply open this up, and we can work through this together if you want. Yep. So
one thing I just pitch in quickly. So
sure.
everyone has the MATLAB drive folder. What you will need to do is copy that folder and then paste it outside the shared folder, because you will not have write access.
Oh, I thought you had already done a hands-on in the morning, so I can
Yeah,
show
I'm just
that.
reminding them, because some people will trip up definitely.
Sure. All right.
So if you encounter an error, just copy and paste the folder somewhere else and work from that.
Yeah. So yeah, if you're getting an error, just maybe say copy this and paste it again in a new folder, and that should work. All right. Yeah. So let's go ahead. So don't worry if you're not able to run it as well right away. So I'd say kind of look at what is being done now, and then you can run it on your own, as well as there are a bunch of examples which you can look at later. Yep. So I'll open up this solution classify ECG signals, this live script, and we'll just open up and we'll just run right through it. Okay. So what is important here, I'd say, is like, again, not focusing on it's not focusing on what function. So for the purpose of this session, I'd say that do not focus on what function is being used where, rather focus on the entire process. And you can go ahead and look at details of the function, and there is enough documentation to kind of learn, and as well as examples to look at. All right. So don't focus on the nitty-gritties, but look at a bigger picture and see if you have any questions there. All right. So yeah, let me just maximize this and let's go ahead. Yeah. So in this case, essentially this is ECG data collected from two categories of subjects. So there are subjects who do not have any abnormality. These are normal subjects. They do not have any abnormalities in their ECGs. And then there are subjects which have who suffer from atrial fibrillation. You can consider this to be like the heart not being able to contract fully, and rather going into a abnormal state where it vibrates sort of, but doesn't kind of pump completely, so that blood is pumped to the rest of the body. All right. So in this case, so we have around 5,000 signals for the normal from the normal data set, while there are 738 or around 750 signals for the abnormal ones. All right. So this data set is publicly available, and it comes from the PhysioNet 2017 challenge, which algorithm from using MATLAB actually won. So let's just load this up. So this data set is available in a MAT file, which is there in the folder. Let's just load this up. So in this case, so we loaded this signal up. All of these are in here. So there is a variable called signals, which contains all of these. And then there is a variable called labels, which is basically the categorization. All right. So let's just look at the first 5 samples here. All right. So what I'm doing is, so if you see, there are around 5,788 in all. So that is the number that you see here, 5788 cross one cell. So each cell is 9,000 samples, or each cell is variable in nature, and then you have the label corresponding to each. So we look at the first 5 labels here. So you can see, you know, there are samples which are 9,000 samples long. Then there are signals which are 18,000 samples long, and so on and so forth. All right, and you have labels which are like, so the first 3 are normal, the next 2 are abnormal. All right. So this is just a sampling. You can vary this very well and see. So say 50 to 55, and in this case again 50 to 55. And if you want to just run this bit, you can, yeah, I'll just introduce like another section break and go ahead with this. Yeah. So again, so all of these are normal. Yep. So now we saw that, you know, there are some which are like 9,000 samples long, and then there are some signals which are like 18,000 samples, and so on and so forth, right? So since we want to kind of have some sort of uniformity before working, like you did in the in the morning, right? So you need some sort of uniformity in the sort of image size that you have, right? So we do the same thing for signals. So we need some sort of uniformity in the sort of signal data or the length of the signals that we have, right? So we'll just go ahead and plot the signal length itself. All right. So we've written a small function to plot the signal length, but it's essentially finding out whether, you know, it's 9,000, 18,000, or so on and so forth. And we'll just go ahead and plot this. Okay. So yeah. So if you see the plot here, you see there are signals which are like, you know, there are some signals from some people which are like 3,000 samples long, or some 4,000, 5,000. So we have almost every, like, you know, there are most of the signals are of length 9,000, while there are some a smaller number which are 18,000 in nature, and then a bunch in between, right? So let's just look at visualizing one of these. All right. So so if you just visualize one of these from the normal and abnormal sets, so you'll see that this is say the normal sinus rhythm, which is like the normal ECG. So you have like a P wave, a QRS complex, as I said, and then a T wave. Okay. And if you look at the abnormal segment, so which has atrial fibrillation, so this does not have the P wave. It has a QRS complex and the T wave. All right. So the P wave is missing because the atria, or the segment of the heart. Yeah. So the atria, or the segment of the heart, the contraction of which creates the P wave, that is not contracting anymore. So the P wave is missing. All right. Yeah. So let's go ahead and maybe like, you know, prepare this data for training. All right. So what we'll do is so as I said, so you could see, like, you know, there were a lot of data sets which were whose length was 9,000, but some were above and some were below, right? So what you can do is you can segment these, you can simply ignore the ones, say, which are less than 9,000, or and whichever ones are greater than 9,000, you can break it down into as many 9,000 sample segments as possible and ignore the remaining samples. So say a signal has 10,000 samples instead of 9,000. So you take the first 9,000 and you ignore the last 1,000 samples. Okay. So if you have, say, something like 18,000 on the other hand, you can break it down into two 9,000 ones. All right. Any questions here on data preparation? So if there are none, I'll just go ahead and you know, plot this again just to highlight things over. So if I plot this again, so this time you'll see that signal lengths are almost 9,000, and we have yeah, so there's just one length. All right. Now the next thing is splitting into training and testing sets. All right. Yeah, why is it segmenting to only 9,000 length signals? Yeah, man. So as I said, so if you looked at the original sort of variation in the length, so you may be aware of, say, image histogram. So this is basically a bar plot showing the length of the signals versus the number of signals having that length, right? So in this case, you saw around 4,000 or 4,250 samples had 4,250 signal samples collected from patients had a length of 9,000 samples. Yeah, I know the the use of samples in terms of signals, and I hope that was not confusing in terms of signals. And so around 4,250 subjects had ECG signals which were 9,000 samples long. Yeah. Yes, so you're essentially choosing the one with the greatest frequency, but you can go ahead and choose 3,000 as well. So there's no limitation there. So we chose 9,000 because it's easier, and this will often happen in the real world when your data set is itself non-uniform in nature. So so you can choose to what you want to do. You can choose to have, say, 6,000 sample lengths and convert everything above 6,000 to that, right? But we chose to keep that because this was the one which was mostly available. All right. So let's move ahead and yeah. Yeah. So let's split the data set into training and testing. Okay. So so we already have our signal labels, right? So we already have our signal labels in the other variable, right? So we have so we have our labels in this variable called labels, and so so what we are doing is we can someone please mute? Yeah, thank you. So yeah, so basically you are splitting the label according to different classes. Okay, so say there are signals which have a label corresponding to the atrial fibrillation. So we we take that signal into, say, a variable called x, afib x, and the labels into afib y, and the normal ones into normal x and normal y. All right. So if I run this, okay, let me just divide this into different segments and just show you the result here. So it's useful to kind of look at that. Yeah. So if you see here, so your AFib X is 718 cells, 718 cross 1 cell. So there are 718 such samples, and your normal X has somewhere like 4,900 samples. Okay. So yeah. So as you can see here, so so you can simply like divide this into like randomly into training and testing sets based on what you have. So you can say divide it into say your training, testing, and and go ahead and do that simply by specifying. So in this case, we have tried to divide it in the ratio of 0.9 is to like 90% to 10%. But you can again vary this as per what you feel is correct. Okay, so 90% of the data is used for training. We haven't used any for validation, and we will use 10% for testing. All right. So yeah, let's go ahead and do this. Okay. So yeah. So you could see, so inside training, you have your abnormal training has 646. Your normal training has 4,000 samples. And similarly, for testing, it's like 72 samples from the abnormal set and 494 samples from the normal set. Right? This is just 10% of what was there. So the earlier it was 718. So sort of some 10% of that. All right. So so if you want to kind of say work with imbalanced data, right? So now there is data which is like in this case you see clearly that the abnormal data you aren't able to collect as much of abnormal data as you can of normal data. This is very typical in the medical setting, but it is also typical for any other applications, say wherein you are say monitoring a device for whether it's working correctly or not, right? So it's very typical to have data imbalance in real world data sets. So a good way to kind of overcome this is a good way to overcome this issue is, as I said, by repeating the abnormal signals multiple times. So what I had said earlier, so so you have around 4,000 normal signals, 4,400 normal signals for training, and only 600 for abnormal signals for training. So what you do is you can simply repeat these 600 signals multiple times, say 7 times, to get a data set which is more evenly balanced. All right. And you can do the same thing with your test data set as well. All right. So as you can see, so for repeating, you're simply using a rep mat, which is like repeat matrix. All right. It's no big issue here. All right. So what you did was, you simply repeated it so that each of your abnormal and normal sets had 4,400 samples, right? So we did some sort of like clever rearrangement to arrive at this number so that both of these have the same number. But like it's very normal. It's to kind of to do something like this. Would it be better if we keep more abnormal signals than normal ones? So again, I would say that depends on the application. So the problem with data imbalance is so you don't want to miss out the abnormal when it happens. So since you had lesser of abnormal signals, so your deep neural network may end up learning only to recognize normal signals, right? So that is why it is essential to have sort of a balance there. You can have a case where you can keep more abnormal signals than the normal one. Then in that case, what would happen is the deep neural network will keep more might mistakenly identify some normal signals also as abnormal for in some cases. Like, so it's like an overabundance of caution. Like, so if you want like a cautious deep neural network, which you're like, it should detect abnormal in each and every case. I don't care even if it classifies some normal times as abnormal, because I don't mind going ahead and checking whether this is it's incorrect or not, right? So in that case, if you want the deep neural network to be overly cautious, then you can go ahead and do that. All right. I hope that answers it. All right. Is that clear, Raghav? Sure. All right. Great. So yeah. So it's 5:30 now. It's 5:37 actually. So I since we have to go up to 6:30, I'll say that, let's before jumping into the architecture and doing the training and so on and so forth, maybe let's just take a brief 3-minute break. And in case you want to stay and ask any questions, I'm happy to kind of do that as well. So. So it's 5:38 now. So let's just take a 2-minute break and do that.
Yeah.
So
Okay,
we'll
sir.
again get maybe a break when we start training, and we can take additional questions then as well. So yeah, please feel free to kind of put in any questions now.
Okay.
Any questions, anyone? Or in case you're if you want to kind of throw ideas against the wall in terms of what projects you can do, so feel free to do so as well. So in the above, we have chosen 9,000 as the segmentation. But in the code, we have not written anything that chooses 9,000 as a segmentation frequency. So if you see this particular function, where is this? Segment signals. Okay. So if you just open this function up, so so this is a function which is there in the same folder. Yeah. So we've just so basically it does nothing. It just kind of takes off the signal length. If the signal length is less than 9,000, ignore the signal. If it is more than 9,000, take the first 9,000 samples. If you are able to take two 9,000 samples, like if it's 18,000 samples or more, then do that. So it's basically that. We've just put it in a more cleaner fashion because it's easier to understand. All right. And again, this is so when you write code, How far do you think we are from developing a neural network having similar parameters as that of a human brain? I would say it's pretty far off. Like, so I don't think if you had that in the morning, but so this is very far off from generalized AI, which is what a human brain is capable of. So deep neural networks, even the ones which are like, which we are working on, and which we like, newer ones which are published each day. So they are still like, they can do one task and they can do that task really well. Now they're awfully good at these tasks, but again, it's very easy to confuse them. So it's very easy to confuse deep neural networks to identify, something wrongly. And in fact, there's an entire research field in dedicated to fooling deep neural networks by, say, providing them with synthetic data of some sense. Okay, so there are fields which spoof this data and try to fool the neural network into thinking that it's detecting something. So however, a human being looking at that same image, which spoofed the deep neural network, might recognize immediately that there's nothing wrong there. But yeah. All right. Yeah, I think we've had a 5-minute break. So let's maybe continue now. Yeah, but keep questions like these coming as well. Like, I'm happy to answer, and in case I'm not able to, like, I'll always park it for later, and we can have that discussion maybe tomorrow, or Dhruv can elaborate on this later. Yep. So yeah. All right, great. So we'll briefly look at, go back to slides a little bit, because I wanted to talk about, like, the architecture. And before, we aren't using CNNs here, but because you've already used them in the morning, so I wanted to kind of highlight LSTMs for a bit. So just wanted to kind of give you a broad overview of what LSTMs do. So we'll just jump into the slides for a bit and then look at this. Okay. Yeah. Yeah. So yeah. So in contrast to, say, CNNs, right? So CNNs work with fixed length data. So you saw AlexNet in the morning, which worked with images of size 227 pixels by 227 pixels by 3, right? So it took in color pixels of that size, color images of that 227 cross 227. So CNNs work with fixed length data, but if you work with variable length sequences, so you look at recurrent neural networks. Okay, so these are primarily used with sequences, and essentially have say they use hidden layers to process future input, and that is where the recurrent nature of that is why the word recurrent comes in. All right. To elaborate on this a bit more, so in your fully connected network and CNN, so they essentially pass the information forward and forget about it. Okay, say you are giving one image to AlexNet and asking it to classify, right? When you give the next image, AlexNet is not really looking at what was given to it earlier. It's doing a fresh sort of computation, right? So in a recurrent neural network, on the other hand, so there is temporal dependency. So they do not simply pass the information and forget about it. So it passes all the information from the previous layer as well, and that is why it is said to have some memory. Okay, as it remembers the past information, remembers how the information it was processing in the past. All right. So it's like this. So if you unroll this through time, okay, if you unroll this recurrent neural network through time, so you can think of it as this. So at each stage, say the first sample x0 was given to the neural network, and it produced output called h0. All right. Now this state of the neural network is passed on to the next, is passed on when it takes on the next sample. All right. And so on and so forth. So this state of the neural network is retained in recurrent neural network. Okay. Now, what happens is if if a sequence is very long, right? Say if a sequence is very long, then the RNN, the recurrent neural network, struggles to pass information from earlier times to the later ones. Okay, so say if this nth sample or tth sample, like it's written here, so if it's too far ahead, what happens is by the time this computation is reached, the state has evolved too far past what it was earlier. All right. So in that case, this information about what was happening is not retained. Okay. So yeah. So this is how if you want to kind of look at it, this is how it kind of highlights. So you have. I hope this retained this sort of color combination sort of thing outlined what was happening. So can we use recurrent neural networks for reinforcement learning as past decisions? Yeah. So definitely, like you can use them in reinforcement learning. But I'd park that to a later discussion, and maybe Dhruv can pitch in on this if you want, Dhruv. Like, do you want to take it up right now, or maybe we can park this for the end of the session?
I'd say it's not really relevant to this one specifically. That's more of a controls thing.
Yeah. Sure. Yeah. So this is basically so as I said, if a sequence is too long, yes, if a sequence is too long, it retains past memory for future reference. But if a sequence is too long, it forgets that past memory, right? Because if a sequence is too long, by the time it gets to this point, this state might have already been lost. So while it retains this information when processing, say, the next some 5 samples or 10 samples, will it retain this information when it is processing the 1000th or 10,000th sample, right? So it might not. So in that case, for long sequences, you suffer from something called a short-term memory or for RNNs. All right, and LSTMs, to overcome this, you came up with networks called LSTMs, or long short-term memory networks. Okay, so we'll not discuss the others, but let's look at LSTMs. Okay. So what LSTMs do is, so it basically does the same thing as an RNN, but it can be considered an extension in the sense that it uses the output from the previous step as well. So earlier, while only the state was being used, it is also using the output. Okay, so as well as the state. Okay, so this memory that it retains, like this memory cell, is called a state, and the state preserves the information and carries it forward in time. Okay, So that creates some sort of this memory which is created, like helps eliminate this problem. Okay. Yeah. So essentially, it enables. I don't want to kind of delve deep into this. So essentially, it enables like you to capture long-term dependencies in this. Okay. Again, you can use LSTMs for regression or classification, and you can go ahead and do that. All right. So yeah. Like, okay, can you explain with an example? Yeah. So I'll try to, instead of an example, I'll try to explain it with this diagram itself. So and then let's jump right into the a real life example. So I think the okay, real life example. I'll not take sure. This is not an example as such, but let me kind of try to give an analogy of sorts. So yeah, exactly. So let me try and give an analogy of sorts. Okay, so say you were, so you have like say you're getting some messages from some number. So you have to coordinate some task. You are getting messages from some number, and what you are doing is, you're calling this number up, you're collecting some details, and you are, say, collecting details for, say, whether a person wants product A versus product B. Okay. Now, what you do is essentially say, you take on you're doing a qualification call, sort of. So on the call, you ask the person a set of questions, and over time you learn that if the person gives this set of answers, then they want object A, and if they give a different set of answers, then they have call object B. But or say, there are a bunch of such options, so they have to so you categorize those. Now suppose so there are, say, instead of object A and B, you have, say, 10 objects. Okay. Now you didn't so suppose the first caller that you had for the day answered questions a certain way, and and they opted for object 9, all right, something of that sort. But you did not note down these answers, all right. Now, for the 100, till the time you get to the 100th caller of your day, you may have forgot that the first person said this, and if they answered these questions a certain way, then they might then they wanted object 9, right? Now, however, if you noted this down, or if you kept a note of this somewhere, or in case you have memory, so to speak, then this sort of classification becomes useful. So I mixed up that analogy quite a bit but I hope the memory part becomes clear there, right? Yeah. Okay, Ashish, if you say so. Yeah. So yeah.
I have an example from my experience.
Sure, Dhruv, go ahead.
If you let me mention. Yeah. So I used to work in wave energy, which is capturing energy from ocean surface waves. So if you think about it, an ocean wave is kind of like a sine wave, right? If you know the past states that you have already seen, you can use that to predict the future. Okay. So what is happening is, if you're seeing a sine wave coming in, which is like an ocean wave, and you know that the peak just passed you by, you now know that the water level is going to fall in the future. So the fact that you can remember the past state which just passed you can use that in order to predict the future, because what happened in the past actually carries over directly to the future. I hope that's a little bit more maybe clearer that way.
Yep. Yeah. So let's so thanks, Dhruv. Let's yeah. Yeah. So what I'll do is I'll possibly kind of, if you look at the documentation for LSTMs, at the end of it, there'll be research papers which kind of, highlight this, and maybe you could go over those. So let me show that at the end of this, after we kind of get to this. Okay. So if you look at the LSTM network architecture, so yeah. So if you look at the LSTM network architecture, so you have your input layer and your LSTM layer. Okay. So your input layer is basically looking at sequences, and your LSTM layers or bi-LSTM layers are looking at the short-term memory networks. Okay. And if you're looking at regression tasks, so it's similar to how you would end in CNNs. So you have a fully connected layer and a regression layer. Or if you're doing a classification task, so you have a fully connected layer, a softmax, and a classification layer. So it's very similar to what you would do in a CNN. It's just that you are replacing the ReLU, the convolutional, the ReLU, and max pooling with sequence sort of layers. Okay. Yeah. Sure. So if you are looking at, say, time series forecasting, so say forecasting share prices or stock market prices, or say forecasting loads which would be appearing on an electrical network, then you could very well go ahead and do that using deep learning. All right. So yeah, let's look at this example, and then maybe this would become clear. So yeah, we'll quickly review where we were. So we had kind of removed the imbalance in our data set, such that both abnormal and normal cases, classes that we had to kind of work with, had around a similar number of samples. So the training data set had 4,400 normal and abnormal each, and the testing data set had around 490 normal and abnormal each. All right. So if you look at LSTMs, so let's go ahead and create an LSTM architecture, right? So let's go ahead and do that in Deep Network Designer, right? So if I open up Deep Network Designer, yeah, so I can go ahead and create a blank network. Yeah. So in this case, you have, so I'll see from the input. So you have your layer library here. From the input, this is a sequence layer which I'm taking in, right? So this is a signal. So you can identify which is the signal here. So I'll just drag that in. Okay. Following that, I have an LSTM which kind of comes in. So I'll just drag in the LSTM layer. Okay. Activations or dropouts, I'll do keep the network very basic, and I'll go ahead and just do a fully connected softmax and a classification layer. All right. So let me go ahead and just connect these and arrange this and analyze it. Okay. So what this does is it will give you a fair idea of whether there are any errors, any changes. So you can see, like, I did not change any default parameters, but you can go ahead and do that as well. Right? Yeah. Yeah. So I can see there are a bunch of questions on CNNs and whether, yeah. So okay, we'll try to kind of answer those, and yeah. So if you look at the LSTM architecture here, we basically defined this in a similar fashion. We dragged in a sequence layer, by LSTM layer, a fully connected softmax and classification layer. The only changes, so when I dragged in the fully connected layer, by default, it took in an output of 10. So I'll just change that to 2. And I'll reanalyze this. And it, yeah, so it works. There are no errors. It kind of has enough input weights, recurrent weights, and biases, and so on and so on. All right. So let's go ahead and define this. So you can see, so I just showed you 2 ways of doing this. So there's you can define it in code using like things like these, or you can go ahead and do this and export it or generate code from here. All right. Essentially, both of this will export to your workspace and give you a variable in the workspace, or if you generate code, it will generate code similar to this. All right. Now, let's look at some training options. Okay. So if you look at the training options, you're essentially defining the same things which you were doing earlier. Okay. So the only things which would change is this time around, you may define the sequence length. Okay. So if you look at the training options in the documentation, and yeah, if you look at training options and its name value pair arguments, which are essentially these arguments. So these are name value pairs. Okay. What is the maximum epoch, and what its value is 10. So these are name value pairs. So if you look at the documentation and go to the name value pair section and look at an option called sequence length. Yeah, just go ahead and do a Control F. Yep. So yeah, so basically you have your sequence length, which gives you an option to pad, truncate, or split input sequences. Okay, so you can go ahead and learn more on the effect and all of these here as well. Like, so you can go ahead and open it in a new tab and just check what kind of what it does. So it is similar to what we were doing earlier with manually with a sort of 9,000 samples, but this is something somewhat different only while training, right? So I'll set the training options. So this creates the variable options here, and what I'll do is, should I go ahead and train this, or should I just? Yeah, let's go ahead and let me see how much time we have. Yeah, let's see if we could kind of train this. If it takes too much time past 5 minutes, and we'll just kind of stop this and go ahead with the regular network, right? So in the meantime, we can take on these questions. So I think Dhruv answered most of them. Yeah. So in which conditions would CNN be effective, since having memory is better? So CNNs are better for 2D images. Yeah. So as Dhruv said, it's signals are usually one-dimensional, images are two-dimensional. So if you're processing signals, you can use CNNs and do that. Like LSTMs, so it's a choice. Again, you can use CNNs or you can use LSTMs. It's both of them have their sort of advanced like pros and cons and you. So whatever I did here with because of using LSTMs, you can convert your 1D data into spectrograms and use CNNs as well. But you know, uh, uh, it will have its own sort of caveats there. Okay, so as I said, why is it showing a single CPU? So I think I have a single CPU. That's why. So I don't have a GPU on mine. So that's why it's a single CPU. But yeah, if you guys have multiple access to GPUs, cloud GPUs, then go ahead and use that. So I'll wait for a couple of minutes, and in the meantime, I'll highlight some examples which you can see for the CNN bit, and then you can go ahead and do that. So Aman says it's showing 62% accuracy. Yes, it's correct, like around 62%. Will hopefully that will rise. So let's wait for that. So in the meantime, uh, you know, the documentation is the best place to kind of get started if you're working with signals and deep learning. So what you can do is simply look at, say, sorting by examples, and then sorting by, say, the toolboxes. So look at deep learning, or you can do a quick search. All right. So now here you can see in the categories, there are like a bunch of things here. So if you see the second or third section here, so deep learning with time series, sequences, and text. So you can simply go ahead and do that. And you can see there are options for sequence classification, time series forecasting, or speech command recognition. So this particular uses CNNs, this uses LSTMs, and there are a bunch of these things which are there. All right. So then I think some of them are for text, but I'd say first, like I think these two examples. So let me just put in the link in the chat itself. So if let me just put this link in, and I think so. Deep learning for time series and signals. So I've just put the link in, and yeah. So you can go ahead and start here as well. So let's look at how much it has trained. Hopefully, it's done a better job than I have. Yeah, so you can see accuracy is not increasing as much. It's somewhere close to just over 50%. I'd say it's not really great an accuracy, because the image. So this is like base accuracy which you'll obtain, right? So this isn't really sort of great in terms of like the accuracy levels. So yeah. Let me see if I can stop this, and stopping this might itself take some time. How can we use it in Microsoft Azure as it provides free cloud computing with our college email? So Dhruv might be the best person to answer that. Dhruv, do you want to kind of take it up while I stop this? Or
Yeah, so we'll have to see with, I mean, what's available with the Azure, what types of instances you have. We can have a follow-up conversation after that,
after this,
after
yeah.
this one.
Sure.
Yeah.
Sure. Are you currently using Microsoft Azure for any sort of courses that you have, Shubham? You could just put that in the chat, then we can follow that up with the faculty as well. Yeah. Yeah, I'll just maybe stop this and yeah, I'll just go ahead with the existing network that I have saved itself. So we did not really get too much here. So as you know, our data set was more or less balanced. So there were 50% instances of it of normal as well as 50% in abnormal. So basically 50-50. So it's essentially this is around that number. So it's not really learning much. What I'll do is I'll go back and let's do it. Let's load a pre-existing like network, a trained network, which we had kind of already worked with, and then look at testing it. Okay. Yeah. So as you said, like your LSTM accuracy comes out to be something like 62%. Okay. So even after training, you'll get something like this accuracy because like uh, uh, because your LSTM accuracy is limited here because you gave the network the sequence or sample data itself. All right. Oh, was there a question? Okay. So you were testing. So because you were creating this basic network and training it, you were your accuracy is quite limited. You may have to play around with the sort of the topology of the network, so to speak, or the different layers in there, and then you could go ahead and see if that helps. Okay, but in a sense, it gives you a network gives you an accuracy around 62. So how can you improve performance? So to improve performance, basically, what you can do is, even though deep learning, you talk about deep learning being end-to-end learning, you can, with no feature extraction involved, you can improve the performance of for deep neural network, especially for signals with like which data, which or features which you're extracting from this. Okay, so in this case, what you'll do is will extract two features, which is the instantaneous frequency as well as spectral entropy. Okay, so we'll extract both of these, and let's see if it's still processing. Yeah. So in this case, so it will extract these multiple features. So that is the instantaneous frequency and the spectral entropy. And if you look at these two features, okay, so if you look at the instantaneous frequency for a normal signal versus that one for atrial fibrillation, so you can see for the normal signal, like the instantaneous frequency keeps varying. So what you're doing is you're taking a window and computing what is the frequency or what is the maximum frequency which is present. Okay, so Whereas for fibrillation, for abnormal atrial fibrillation signals, you can see there are places where the signal frequency drops quite low, and again, like for larger amounts of time, and there is also somewhat of a more regularity here in comparison to the normal one, right? And if you look at the spectral entropy, again, there are some clear differences between like these two, like say the range itself, or what you can say the variation in this. All right. So so you can simply compute these instantaneous frequency and spectral entropy for these signals. Okay, and yeah, this one. Yeah, so we'll just wait for this to get over, and so in the meantime, what you can do is I'll just go ahead and highlight the code, and then maybe you can look at that. Okay, so what we are doing is essentially computing the entropy as well as the instantaneous frequency, and adding that to your feature vector. Okay, so in this case, our feature vector kind of like adds to like you just simply concatenate these sort of arrays and add it to these cells. Okay, so so it's yeah. So in this case, yeah.
Do you want me to share the screen or?
Dhruv, can you run this quicker? Then if you can run this quicker, then I think it would be useful if you could do that.
Yeah, it's training fine on my one.
Sure, sure.
Can the host make me the presenter temporarily?
Let me see if I can do that from my end. I should be able to. Yeah, I can. I've just passed on the privileges to you. So
Okay, let me try.
yeah.
Yeah, so I've got a slightly faster laptop, so it runs a bit better.
Sure. Let me know if you want me to cover the ending bit again on the presentation. Yeah.
I think I've just loaded up the extracted features. If you just want to mention what we've done to the architecture, and then the training is already done here. So. Can you hear me? I think Praful might have been muted by accident. Can we get him back?
Yeah. Thank you. Yeah. Yeah, Dhruv.
Yeah, now you're audible, Praful.
Yes. Yeah. Yeah. Do you want me to walk through it, or I think that I can just walk through this and maybe you can just progress it. Yeah. Yeah. So
right, which bit do you want me to run?
yeah, I think you can run everything up to the standardization of that data. Yeah. You can run everything up to this. Yeah. And yeah, any other questions? Sorry for the sort of mix up here.
Okay, yeah, I think it's run now.
Sure. So yeah, so essentially what you're doing is so you kind of created these. You went from providing these inputs by themselves to the sequence input itself to say computing these uh, variables like your entropy and your instantaneous frequency, and these have a length of 2 cross 250. These are length of of 255 samples itself. Okay, and so 1 cross 155 is your instantaneous frequency, and the other 1 cross 155 is your entropy. Okay, so if you could, so now what you can do is you can modify your architecture as well. Okay, so since we extracted two features, our dimensions, our signals have two dimensions as well. So what you can do is you can simply change the number of sequence inputs to 2. Okay, so in this case, what we're doing is instead of giving the signal itself to your network, you're simply giving the feature vector itself as the signal. Okay, so in this case, the length of the signal now becomes 255. Okay, and you're giving that. All right. So where you can change this is you can simply change this in code by saying 2, or if you go to Deep Network Designer, you will get that option of having it as a 2 sequence input as well. All right. So there should be on the right hand side in properties, you can simply define the input size as 2. All right. So again,
do you want to show that, or?
yeah, Dhruv, I think if you could show that and drag drop this network, or just maybe run this bit and show that network in Deep Network Designer, I think that would be useful.
Okay. Yeah, meanwhile, you can carry on discussing the training options if you want.
Sure. Thanks. Yeah. So other than that, I think we can specify a similar training options. We haven't really changed it around much, and we can simply go ahead and do that. Yeah. So Dhruv's just looked at the sequence input. So you can see again, it still has 5 layers, but it's just, you can see the property that he has highlighted. So he's made it 2, and that's we changed. It was 1 initially. It's just changed to 2 now, and we've just computed the features. Okay. So that's the only change, only major change, I'd say. All right. I think we could get back to just showing the loaded network, and or if you want to train it and it trains fast, you can go ahead and do that as well through the training options and this bit. Yeah. So yeah. Yeah. So as you can see, it pretty much overcomes the 60% mark right away, and yeah, so although it kind of goes back down, but it'll come back up, and yeah.
So basically, I mean, the network's just trying to adjust the weights, right? So it's trying to find the right value, and eventually it should go all the way up.
Yeah. So we have quite it's training for 10 epochs. So so it's like, it's still halfway there itself. So all right. Yeah, I think you can. It's already touching 90, so it's pretty good in comparison to the previous one, and yeah. So any questions on this in this case? Like, was this clear, and was this useful in seeing how it is different from like processing images, and you might still end up needing to do some sort of feature extraction here, and because feature extraction, even though they say might not be necessary in deep learning, but it still has its own value. Yeah. Why aren't we using the validation data set here? So it's basically sort of a yes no sort of problem. You can choose to do validation as well. Like, in that case, it will just go ahead and use the validation set as well. It's no biggie. Like, it's a like so we aren't really using it, but you can go ahead and use it. We mentioned that percentage as 0. You can go ahead and change it and add those variables in, and it should be quite okay. So
I think one more thing is data set works well when you have images because you're loading lots of different images. Here you're testing with almost the same set of signals again and again, and just trying to adjust the weights inside the LSTM. So
exactly,
it has more value for images. I don't know why the network accuracy has not gone higher. Maybe we need to adjust the learning rate or something.
Yeah. I think it came up to 90 and then again dropped down because of some reasons or the other.
Just try with the smaller one.
Sure.
While we're taking questions, this can just keep running.
Yeah. So there are a couple of questions on, you said feature extraction has its value, but it's not necessary. So as I said, like, do you overfitting might be a cause for drop? No, not really. So in case of images, so images or image classification problems that you kind of did in the morning. So there are, as Dhruv said, there can be a wide range of these images which are available, right? So a single image of a car might be taken against a bunch of backgrounds, right? So that's where validation might really be useful. While here, because you're classifying between just these two classes, you can go ahead and keep validation, but because it is a very sort of predictable sort of signal, there isn't as wide a range in variation with signals as there is from in images. That's why. So overfitting, I doubt it might be overfitting because there are, again, like, just two classes, similar range of signals. So it's not. I doubt it might be overfitting. Yeah. Any other questions? So I think we have just maybe 2 to 3 minutes. We might. Yeah. So I think this presentation was mostly it, and I just have a couple more slides, and
Okay, yeah, maybe we can just see if this reaches a higher accuracy. Otherwise, there might be something wrong with
sure.
the data set I have, because yours
Sure,
seem to be doing much higher before.
Sure. Yeah. I think we can just maybe.
Anyway, I'll stop this and we can get back to you.
Sure.
How do I give you the images?
Maybe just right click and yeah. Thanks, Dhruv. Yeah. Let me just start sharing again, and yeah. So as I said, so as I said, we saw how you could use LSTMs and you could handle unbalanced data sets, and you could also improve your feature performance with feature extraction. Again, so the main takeaway that I want to kind of highlight is, so feature extraction is not dead, so to speak, and feature extraction prior to training can improve your accuracy. as well as your models may not perform very well on raw data in case of signals. And so while images are good and they might be a chunk of deep learning focus, your signals are quite like as important, right? So I think we covered most of these first three steps here, and now let's just briefly talk about like model integration with systems. Okay, so when working with signals like this, right? The one thing is you can readily deploy and scale your machine learning or deep learning with MATLAB. So we already saw how like I was on a single CPU, Dhruv on a GPU. So we already saw how it could scale up while we did not really need to make any sort of big changes there, and it could scale to a GPU pretty seamlessly. It can scale up to enterprise or cloud systems as well. So we'll try to get back on that question that you had, some of you had for using cloud systems. So now so if imagine an application that we just saw, which we just did, right? So we have this say ECG signals coming in, and this is a very typical application which we can see right now coming into play because these health monitors and fitness bands have become so commonplace. So these monitors with ECG or detection might still be somewhat on the higher price range, but they are collecting this data in real time, right? And so they need this sort of processing to also happen in real time. And this is where it is essential for you to not just develop these algorithms on the computer and for them not to be sitting on this computer, but you have to kind of take that next step forward and take this MATLAB code and deploy it to an appropriate target. Okay, so you can either auto-generate C, C++ code for your embedded systems or CUDA code for your GPUs, or you can target a bunch of other CPUs, ARM CPUs, or FPGAs, or SoC devices, wherein you have a combination of these sort of platforms. All right, and again, like if you're working with in enterprise, so many of these industries and many industry customers, such as so they regularly monitor signals from their physical assets. So these assets can be anything from, say, a wind turbine to a drilling rig and so on and so forth. Okay, and these assets are constantly sending in these signals to their servers, and they are making decisions like these every moment to see whether the asset should be kept running, whether the asset should be stopped in sort of under some conditions, like say a storm or wind speed going higher than a particular threshold, then maybe stop the wind turbine for the time being, or say stop drilling if you detect seismic signals elsewhere, and so on and so forth. Okay, so I know I did not work much on this, did not talk much on this, but there are very good examples, and this is better done if you have access to like some hardware which you can do this readily on, and it's more effective a presentation then. All right, so deep learning in MATLAB has come a long way. I'll leave you with this. So from 2016 when it was first introduced to 2020, it has come a long way in terms of how capable it is, as well as how you can apply it to across different domains. And what I want to highlight is currently in MATLAB you have over 200 examples, over 200 examples across different domains. So whether that be just simple image classification to something like regression on time series data, you have all of these, and these are really good starting points for you to kind of work with. Okay. So I'm sure Dhruv showed you the deep learning on-ramp earlier, and you have access to deep learning training courses as well. So please go ahead and use this. So I'll just highlight this again in case some of you are still wondering. So you have deep learning on-ramp, which should be like your first result if you type it in on a simple Google search, as well as if you go on to MATLAB Academy, you should get access to, say, a longer course on deep learning with MATLAB. So
Prapul sir, can you share this link into the chat box so the participant can easily go through it?
Sure. Let me do that right away, sir. Yeah. So I'll just put both of these in. So I think here this is possibly focused on images, deep learning on-ramp, but on the longer training, you might have some signal components to it as well. Okay, let me put that again. For some reason, it came out one after the other. So yeah, so I think I put the corrected links in. So yeah, so that's all I had from my end. So this is my email, and I'm sure let me put that in as well. And in case you're sort of beginning work on some such domains, then please feel free to kind of drop us an email, or you can drop Dhruv an email, and we'll try and help however we can. Yeah. So that's all I had time for, sir. So in case you have, yeah.
Thank you, Prapul sir, and Dr. Prapul and Dr. Dhruv for their kind and the informative lecture they have taken, and I hope the participant has get some answer their question they have, and we will meet you tomorrow with the Dhruv sir. And regarding the on-ramp, the sir have already shared the link in the chat box, and the volunteer please share this link in the group so that they can easily pursue their on-ramp. So thank you once again, sir.
Sure, Professor. Yeah.
Thank you, everyone.
Thank you. Have a nice evening, and we'll see you tomorrow morning.
Yeah, thank you, sir. Thank you.
Thank you.
Thank you. Take care.